You're listening to Brainwork Framework, a business and marketing podcast, brought to you by focus-biz.com.
Hi, everybody. Welcome to this episode. With me today is a very special guest who's going to talk about algorithms and game theory. Literally, these are all around us in everyday life, even if we realize it or not. With me today is a gentleman who brings tons of experience in software development, programming, process improvement with Six Sigma, and owns his own company, CoorDisc. Noah Healy, thank you so much for joining me today. How are you?
Thanks for having me here, Chris. I'm doing well.
Wonderful. So tell me about your past experience and what you're doing today with CoreDisc. I mean, you bring a lot of past experience in a lot of really cool topics. Some might call them nerdy, but I think they're cool. A lot of other people think they're cool. Tell me about your past experience and what you're doing today.
Well, CoreDisc basically started almost 15 years ago, although it hadn't really gotten to that point where I was working for a company and had effectively completely automated the job for which I was hired. And that company had no career prospects for anybody, actually. So I had some money, and so I left and decided to kind of take some time to think. My major interest is computational mathematics. So I did a little bit of traveling and a lot of thinking. And near the tail end of that tenure of time, about a decade ago at this point, I came up with this idea for finding consensus among networked people or agents. In game theory, we talk more of agents than people, because that allows us to model environments as elements of a game, or increasingly computer agents as elements.
Interesting. So what is gamification? I mean, we're hearing more and more about it, and I don't think it was really used that often, or at least the way that it's used today has shifted. It's evolved, hasn't it?
It has, and gamification and game theory have some overlaps, but they're not exactly the same topic. Gamification in game theory, it's all about motivations. So the basic notion around game theory is that some situation will be the outcome of multiple independent agents' decisions. And each of those agents' decisions are driven by their own interests, not the outcome of the game, not the interests of other players, just their own interests. And
Oh,
so historically, a lot of game theory, particularly during its inception, was basically around life or death, or in some cases, more or less money. But with gamification, we recognize that human beings, at the very least, tend to have more interests than simple survival or suicide or more or less money. And
mhm.
so it becomes possible to design a system where individuals will behave in ways that make that system go in exchange for rewards that the system designer is willing to part with.
Wow, that's so fascinating. The way that psychology and human behavior play a role in just how we interact with people, what decisions we make, how we think, and the way that it can be, I don't know, is it put into an equation in a sense? Is there literally just a science and a formula behind this game theory?
So there is, the model gets very complicated very quickly. So let's put this in context and start very small. Imagine a two-player game. So you and I are going to play a game, and each of us is going to choose one of two things. So if this game is sort of interesting, there's four distinct outcomes. Let's say we're each going to say either 1 or 0. There's the both of us say 1, there's the you say 1 and I don't, there's the I say 1 and you don't, and then both of us say 0. Okay, so there's four different outcomes. Well, you have your own interests. So if these outcomes are all distinct, you can have 4 factorial or 24 different ways that you could have an interest in the way these outcomes come out. And I could also have up to 4 factorial different ways that I could be interested in these outcomes coming. So at the very sort of naive level, there'd be, I'm sorry, 24. 24 times 24, which is, what is that? Six? Yeah, that's right. 576 of these games. Now, there's certain symmetries that are involved in that, and where if we don't care which player is which. But let's take a look at two different extra possibilities staying at the naive level. Adding a third choice and adding a third player. So if the two of us were going to play a game again, but instead of having two choices, we each had three choices. Now there's 9 possible outcomes, right?
Uh-huh.
Because you can do one of three things. I can do one of three things, 3 times 3. Okay. 9 factorial is like 380,000. So you could have any one of those 380,000. I can have any one of my 380,000 and change. So we multiply those two numbers together, and suddenly we're up in the, a sixth of a trillion range-ish of how many games there are. Let's, instead of adding a third choice for the two of us, let's add a third player.
Uh-huh.
So we get Alice in here. She's got 2 choices. So 2, 2, 2, there's 8 different games. So this isn't so bad. It's not this 380 business. It's only 8 factorial, which is like 40,000. Okay, and some change. But there's 3 of us, so it's 40,000 cubed. So instead of like a sixth of a trillion, now we're talking about like 70 trillion of those games. So the formula, if you're gonna try to use this formulaic thing to describe every possible game, by the time you get to things that involve 5 or 6 people that have 5 or 6 choices, you're going to run out of atoms in the universe long before you finish writing things down.
Yes.
Now, fortunately, that's the naive version. There's some vast simplifications, and of course, that's the space of all possible games. Any specific game is only one of them, but still, one specific 5-player game would be represented by a 5-dimensional array
Mhm.
of the 5 choices each of these 5 players can make, where every entry in the array would have 5 entries describing how each person felt about that particular outcome. And there are mathematical tools that are actually built into Excel, for example, where you can build these things into, you could write that model down. That would be a pretty large model to have to write down. 5 to the 6th power is, let's see, is that the 200? It's like 2 million-ish, about.
Oh,
So if you were keying that in by hand, it would take you a little while. But efficient algorithms exist that will tell you what the sort of equilibrium strategies are if they exist.
that's so crazy. Just taking something that is like, okay, choice A or B, how many players you have and how quickly that can escalate into all the possibilities. You can't even code that, right? I mean, there has to be something else out there that is going to achieve the outcome that kind of factors in all of those decisions that could be made along the way.
Well, that's where the power of the geniuses that have been working in this field, who aren't me, really come in. So there's a couple of very powerful simplifications that exist. One of them is something called evolutionary game theory. So you can create a game that has lots and lots and lots of players, but only a handful of roles. And we were talking about games in terms of single moves, basically, but many games can be played over and over and over again, or have a certain depth of activity, which of course also creates entire super exponential explosions. But if you have a game with sort of a limited set of roles that you play over and over and over again, there's effectively an evolutionary feedback where players in a role will do what they want to do, because that's the entire point. But then they get feedback from the game itself. They wind up with the outcome they wind up with as a result of the other roles doing what they want to do. And they'll learn from that. So if you do what you want to do and it turns out very badly for you, and you might change your mind about what you want to do next to try to get to somewhere where things aren't so bad for you. And so evolutionary games actually also cohere to this equilibrium behavior, uh, or can have multi-stable or chaotic equilibrium behavior if that's the kind of game it is. Um, but this means that because the pattern of having roles in repeated behavior creates these evolutionary equilibriums, we can actually design games based on roles and sort of balance out the rewards in order to create the sorts of long-term behaviors we're interested in. And that's sort of taking the equation and running it in the other direction.
Wow, that's so fascinating. What was something that surprised you when you were learning about game theory and just the development of software? Was there something that just completely blew your mind?
Virtually every single aspect of computational mathematics is totally mind-blowing. The very core proof that kicked this entire thing off in the first place is this deep and profound idea. But there's a thing called the story of Mel. If you search for it online, you'll find it. And it's a certain amount of inside baseball because there's a lot of references that are hard to understand unless you've programmed computers yourself. But the core story is this tale of one of the most impressive intellectual feats imaginable. And it's about this programmer named Mel. And it's told first person from the point of view of this guy who had gotten out of college and joined a computing firm. And in these days, it was before operating systems. So when companies developed computers, they would also develop the programs and tools that would run on those computers. And that computer plus its software plus its operating system would essentially be a complete unit. And when you bought a new version, you'd effectively throw away all your code and data and everything else and basically start all over again with a new computer.
Wow.
And this company was trying to put together something like an operating system, but their chief programmer, Mel, hadn't been to college. He had just sort of self-taught and was obsessive and had learned how to use these things. And the system used what was known as a drum memory. So that's similar to the hard drives that still exist on some computers. But instead of using that as a storage, that was the main memory. There was a spinning drum that reader head would go around and could read the locations on the thing. And the way it worked is it would read two words. So it would read one word as either an instruction or data, and then it would read the second word, and that was a pointer, a map, basically, to where the next word it should look for. And so the computer would go do the thing, and then the drum would be spinning. And once it got done with the thing, it would seek out that next location to get its next instruction. Mel was so intimately aware of how this thing worked that he would put his instructions on the drum so that when the time came to read the next instruction, the head was already there. It didn't have to look anywhere because he would time out. He'd figure out where the drum was going to be and he'd put in the map to where that location was so that when it did its lookup, it would be done and it would already be there. Except when he needed a delay. And then he'd put it in the one behind it so that the thing had to spin one full revolution to give him some extra time for spacing. Another trick that he did was that he'd write loops that were infinite loops. They had no exit condition.
Mhm.
But the system could write numbers into this thing. And one of the problems with computers that you may have heard of is an overflow error. So computers basically can store numbers that are up to a certain size. If they try to store a number that's larger than that size, the sort of 100's okay, 1000's okay, 10,000 registers is zero because the one falls off the end, that kind of thing. Mel would actually have his loop counter up updating the bit after the map instruction so that when the loop counter overflowed, it would change the value of the map instruction at the end of the loop to go to where the next point in the loop was. So he didn't actually have to write a loop test.
Wow.
Also, the codes, so the instructions that say, add numbers or find something and pull it off the disk, stuff like that, are all just numbers. And so whenever Mel needed a special number, let's say for some reason this algorithm needed a 57, and he happened to know that 57 was multiplication, the multiplication sign, he would find a multiplication sign that was in sort of a good place and just tell it to read that as data. So it would use that multiplication sign as a 57 instead of having to use up a whole nother spot in the memory to keep a 57 in.
And how long ago was that? When did Mel put
This
that in place?
this would have been with drum memory. This would have been probably early 60s, maybe late 50s. And our protagonist who's writing about these things, the premier program of this company is a blackjack program. So they can go to trade shows and people can play blackjack against the machine. And the salespeople ask Mel to create a mode bit. They basically want a button on the machine and they can press the button and the machine will cheat so that the player always wins blackjack. And Mel really doesn't want to do that. He feels like it would be unethical.
Yeah.
But the boss asks him really nicely and he takes a shot at it. When it gets done, when they press the button, it cheats and it never lets the player win. And so Mel says, that's just because, my soul is so ethical that I couldn't be forced to do it, and refuses to work on the project anymore. So the boss tells the kid who's writing all this down, hey, do you want to take a look at what Mel did and see if you can fix it? So that's where it really gets in the meat, and we start hearing about these stories of the things I've been telling you about, how absurdly crazy Mel's programming style was. And so, yeah, the kid gets into it. He's in there for like a week, and then he goes to the boss. He's like, there's just no way. And the boss is like, yeah, I had to ask. I wasn't expecting any.
Wow. And all of these new advancements and twists that Mel brought to tech and computing industry, what did that affect going forward? Was there a change in how we were able to access and use data?
Well, the major effect of those early computer pioneers was figuring out that while the capacities of these things at efficiency scale was truly ridiculous, the complexity of that wasn't sort of worth the trouble. So this is essentially the earliest story of technical debt, which is a term that gets thrown around these days, where you can make something that does what you want it to do today. But if you also wanted to do anything else tomorrow, what you did today might stop you from being able to do that without starting over again from scratch.
Wow. That's crazy. Now, how does this all tie in together with the game theory you mentioned and algorithms in the context of economics and finance?
Well, this ties into algorithms because this essentially shows the powers and perils of algorithmic design. The Mel algorithms are effective. I mean, he creates this convincing blackjack game, but they're so intricate that they're too specialized for general use. Mel doesn't want to make your sales version, and he apparently can't, and he absolutely won't. So you can't have your sales version because you can't create a sales version of this thing because the system's so intricate that unless you're the kind of obsessive genius that Mel was, you can't use it. So what we're concentrating on for the last 60 plus years is making these tools easier and easier to access. Unfortunately, this does virtually nothing about the technical debt issue. And so think about how many 10,000 entry spreadsheets with things going all over the place that the equivalent person 50 years ago never would have built a ledger that was that complicated.
Mm-hmm.
But there's a very, very unknowable edge, basically, where You go from everything's fine and everything's understandable and you can use it and it does what you want it to do and you can change things and they do what you want them to do. And then one day all that goes away and suddenly it doesn't do what you want it to do anymore and you don't understand it and you can't change it in ways that cause it to become understandable. And so to some extent, the most important lesson from these things in algorithms is simplicity. Your algorithms can be very sophisticated, but they need to have this core of mathematical purity in order to be dependable enough for us to be able to actually rely on them. And sadly, nobody actually does that. All the companies that exist are essentially building little Mel islands for themselves. And while Amazon and Google and the New York Stock Exchange don't appear as of like this exact instant to have gone over the edge, you don't really get to know when you've gone over the edge. It's not always immediately obvious.
Because the problem just keeps compounding and you're like, okay, this got way out of hand. It got more complex than we imagined.
Right. Well, that's another fun mind blow. So we talked about how unbelievably rapid game theoretic systems grow. So let's talk a little bit about how fast Turing machines grow. So Turing machines are a state machine. And so each state has the ability to take in a piece of data off of a paper tape. Let's restrict ourselves to just binary.
Mhm.
So there's two different pieces of data. And as a result of that, it can either delete, rewrite, or leave alone that data. So it's got three choices. It can move to the left, move to the right, or stay still. So it's got 9 choices, 3 times 3.
Uh-huh.
And it move to another state that's in the machine. So there's 9 one-state Turing machines. But once you get to two-state Turing machines, well, there's 18 choices for the first state and 18 choices for the second state. So that's 18 squared. So that's 324. But with a three-state Turing machine, there's 27 choices for the first, 27 for the second, 27 for the third. That's 27 cubed, which is like 3 to the 9th power. So that's up around like what, a few 100,000. And then with 4, you'd get 36 to the 4th power. So that's 6 to the 8th. Oh, that's well over, that's into the tens of billions at that point. And that's not even the bad part, because there's this other thing called the busy beaver number. So the busy beaver number asks, given a Turing machine that's binary and with a given number of states, how many ones can it output on a blank tape and then stop? And that number grows so fast, we literally cannot imagine how fast it grows. It's that number, that sequence is known as something that's incomputable. And that means that while there's some level at which we can figure out what those numbers are, at some point, and we can't figure out what that point is, but it's fairly small, we will not be able to figure out what those numbers are anymore, because figuring out what those numbers are is formally impossible, mathematically speaking.
Wow. And this is coming straight from the guy who was just able to do like 46 times 23 and then 9 cubed in the air. Like he's looking at a fictitious whiteboard and he's literally pulling the numbers and he's like, oh yeah, that's like 330,000. No big deal. Like that's crazy.
Well, these numbers are small. To give you a basic sense of these numbers, the first one is 1, the second one is 3. The fourth one, we used to think that we knew what it was, and then somebody figured out how to make it 4,096, and we are no longer confident that that's what it is. The fifth number is, there's something called a power tower. So exponentiation, like 2 to the 3rd power is 8, and 2 to the 4th power is 16. But imagine if you just kept piling up exponents. So 2 to the 2 to the 2, you evaluate from the top down. So 2 squared is 4, 2 to the fourth is 16. That's not a big deal. Let's put another 2 up there. Well, we just found out that 3 2s is 16, 2 to the 16th is 65,536. That was max int back when I was a kid, or one more anyway. So that's a nice step. We put another 2 on there. It's 2 to the power of 65,536, which is a number that has somewhere in the neighborhood of 19,000 plus digits. So this number grows very, very quickly. The fifth Busy Beaver number is at least a power tower of tens that's somewhere between like 15 and 20 tall.
Wow.
And to put that in perspective, 3 tens in a power tower dwarfs a Google. So a Google is a 1 with 100 zeros after it. The third power tower of 10 is a 1 with 10 billion zeros after it.
Wow. Wow. That's just crazy. It's blowing my mind on that. Now, tell me more about how you're using all of that experience, all of that knowledge with CoreDisc, to create better markets, wealthier world. What happens with that? How is that working?
Well, the basic idea is to actually reevaluate economics in terms of this game theory and in terms of these algorithms. So the basic problem of the marketplace is finding and disseminating information, which is what we use the internet for.
Mhm.
And it's not large amounts of information either. Prices are relatively small numbers, certainly much smaller than these beaver numbers I was just talking about. And basically everybody is agreeing on them. So it's a small number that you can send one copy of to everybody. It's pretty cheap from that perspective.
Mhm.
The thing that's expensive about it is everybody wants to lie about it.
Why?
So you might be familiar with the LIBOR scandal from around a decade plus ago, but it- you don't really need that. Imagine if when you go to the grocery store, instead of having prices labeled on everything, instead there was a negotiation. And the rules of the negotiation were that the grocery store would tell you what it cost them to actually have that item on the shelf, and you would tell them how much you needed it, like what the absolute top dollar price you could afford to pay. And you would just average those two numbers together.
Oh, wow.
Okay, well, what if you didn't tell the truth? What if you lied? You might be able to get all of your groceries cheaper. What if they lied? They might be able to sell everything for more money. So everybody's incented to lie about their own personal stake, about their own personal consumption. Because if the other person is in a position to be generous or in a position to be desperate, then that lie will benefit you. And lots of people are in positions to be either desperate or generous. So that's the problem. So, how do you rearrange the game so that you can figure out what this is where everyone's incented to lie? Well, one key thing, and this is how markets actually work, is that the lies to some extent cancel each other out. So, all the people who want to buy for too little and all the people who want to sell for too much balance off against each other, and the average of their things is still pretty close to the average of what they actually want. And that's more or less where market averages come from. But there's not really enough of that going on to get the averages to average out. So what happens is people come in who want to buy and sell. And so they have interests in sort of trying to create desperation so they can pick off people at their worst possible cases. And with computers, increasing speeds, increasing awareness, increasing just noise in the system, it becomes easier to create that desperation and easier to sort of push people into these not ideal deals. And so that's what we've been seeing over the course of the last 40-ish plus years with the computerization of the marketplaces, is that the financial system as a whole has become more and more and more expensive. And they're still just producing this relatively small price number that relatively large numbers of people are all looking at the same time. So, so that part is still the same. It's just how much we're spending to get that part that's going up. And this is what's known as a red queen's race. This is another game theory concept.
Okay.
So the red queen's race comes from Alice through the looking glass. Alice meets the red queen and has several impossible things happen to her before breakfast. And at one point they have a race and she and Alice set off running, and Alice realizes that they're not really making any progress. And the queen says, of course, you have to run as fast as possible just to stand still. In an evolutionary environment, if you have a purely competitive activity, if one side gets stronger, they can dominate. But if both sides get stronger at the same time, the equilibrium can remain where it is. And so by having this sort of floating group that is switching sides in order to keep both sides just as strong as each other, what you get is this situation where the equilibrium staying exactly where it is, but the amount of pressure pushing on it is increasing. And the cost of that pressure is increasing. And so we get higher and higher costs for the same actual outcome.
Wow, that's so crazy.
So what I did was essentially found the obverse of that system. This is a handy mathematical concept where basically if you reverse literally everything, you get something that works exactly the same, except every single part of it's perfectly backwards. And so my system, instead of having people make whatever deals they can make and sort of propose things in the ether to try to catch deals, what they do is they propose whatever prices they want. The system integrates all those price information together into that singleton price that everybody gets to see. And then you see how many deals that price attracts. And since the money that you make on the speculation side of things is related to how accurate your outcome is, the incentive for you to lie about your own personal circumstances vanishes, because what you want to do is tell the truth about how you see the world, because that's the highest rate of return you can earn.
That's so incredible. Do you think that there's market manipulation in the world today? And
Undoubtedly.
yeah, and your system removes that, right? It removes the incentive to lie at least.
Yeah, I wouldn't say removes, because there are non-economic motives for some of these things,
Mm.
but it removes the economic incentives for doing so, which are, as far as we can tell, the primary incentives for doing those kinds of things.
That's so incredible. Man, if you could take that and benefit the financial markets in such a way, can you help with any other place? My thought is politics. How can we take out that crazy incentive to lie, make them want to be more truthful, and take that pressure off, reverse it? I don't know. I just feel like your
Well,
brain can benefit so many industries.
politics is extremely tricky because politics is intrinsically combative.
Hmm.
We have a phrase, all's fair in love and war. And we've also have thinkers on sort of war and politics going back millennia across many cultures. Sun Tzu, all war begins in deception, or is rooted in deception.
Hmm.
So the thing about conflict-based games is that they're very resistant to this sort of behavior. One point that is worth thinking about, you may have heard of something called the prisoner's dilemma. And this is a little toy model game theory game to explain a basic point of strategic reality. So the prisoner's dilemma is a tale about two criminals. They've gone out and they robbed a bank. They've each been caught, and they're each being independently sweated in the interrogation room.
Hmm.
And they have a choice. They can stay loyal or they can betray their partner.
Mhm.
If they both stay loyal, they've both been brought in, they're both going to do a little bit of time. If one of them betrays the other one, then the betrayer gets away scot free, but the betrayed gets hit pretty hard. But if they both betray, then they both get hit really hard. Well, this model is interesting because it creates a scenario where each individual's best interest is to betray the other person. And from TV and actual reality, a lot of our justice system is actually based around this concept of self-incrimination or betrayal among groups. Going back to evolutionary game theory and playing this game over and over and over again, if there's going to be a tomorrow, if you're going to have to see that guy again and maybe work with him or other people who are going to know what happened, staying loyal actually starts to dominate, because the best outcome that can happen to you is that you both stay loyal, you keep the swag, you have to do a little bit, but you're out and you get to keep the gains. And so prisoner's dilemma is actually a mechanism to essentially create cartel behavior where illegal conspiracies will spontaneously form if you're offering the players prisoner dilemma type situations. And unfortunately, our current political institutions also offer the ambitious a prisoner's dilemma option in terms of cooperation versus reneging against their politically ambitious fields.
Wow. That makes so much sense, though.
Yeah, we've basically created a system that's designed to turn them into coherent groups that are counter to our interest. And the alternative would be another simple game called chicken, where you win if you try to win, unless somebody else also tries to win, and then you both lose. So in chicken, it's very similar to the model of the prisoner's dilemma, but instead of there being a both of you can win outcome, there's a both of you can lose okay, where you both exhibit cowardice, and there's both of you lose badly, where neither of you exhibit cowardice. And chicken is a lot harder to form cartel cooperative behavior among its participants. You can do it over time where you have some kind of coded agreement, like I'll go down this time and you'll go down next time, that kind of behavior. But that's much, much more complicated than just when they ask me about the deal, I'm keeping my mouth shut and you'll keep your mouth shut when they ask you about my deal.
Right. That's so crazy. But the way that you described it and broke that down, it makes so much sense. What are the incentives for them to tell the truth versus lie? And you're looking at this situation, the human behavior, from such an objective standpoint, and it makes so much sense.
Well, that's game theory. I commonly call it the most flippantly named thing in human history. Game theory is the mathematics of strategy, and computational theory might be one of the most obtusely named things in human history. It's the mathematics of philosophy.
Oh, such good information. I love this. This is wonderful. Now, Noah, where can people find out more about you and CoreDisc?
Well, to find out about me, you can reach out to me on LinkedIn. I'm the Noah Healy there, or in person, Noah P. Healy at yahoo.com. I've recently launched a podcast with the former CTO of Reddit, Marty Wiener, called The Fourth Age, and that's up on Google, Apple, Spotify, and several other platforms. So if you want to learn more about AI and sort of the game theory of how to manage things that are not us, but capable of complicated action, we talk about that kind of stuff. To learn more about CoorDisc, again, you can reach out to me, but there's also a website, CoorDisc, and also just searching for coordinated discovery markets, which is where I got the name. That's a unique enough idea that it mostly refers to me. So a quick Google search will find the website, me, a bunch of other stuff about CoorDisc.
Like anytime you search coordinated discovery market, Noah's your guy. He's the one who pops up.
Yeah, it's like the first 4 or 5 entries.
Nice. That's brilliant. And I love that you have your podcast coming up. Sounds like great conversations and topics that you're going to be covering. I am going to go check that out right now. How many episodes are out so far, or is it coming through soon?
Let's see. I believe we've got 5 episodes out right now, and I need to finish curating. Marty has edited the 6th, and he wants my approvals. I need to get my butt in gear, so there'll be a 6th episode.
Nice. I love it. Thank you so much for joining us today and sharing all of just the wealth of knowledge and experience that you have. I really hope we can have you on again sometime in the future as technology and things advance and change. But Noah, thank you so much for your time and your insight here. This was incredible. Thank you.
Thank you.
Absolutely. Feel free to follow, like, and share the podcast, and make sure to continue checking us out for more incredible guests. Noah Healy, thank you so much. Hope you have a great rest of your day.
Thanks again, Chris.
Thank you.